simple stuff. So magnets, you learn that magnets produce magnetic fields. Well, I just told you something else. What produces magnetic fields?
Moving charges.
Moving charges. So if a magnet is producing magnetic fields, it must have moving charges in it. Where are the moving charges in the magnet?
Inside the magnet. Inside of the magnet.
What is inside of the magnet?
Electrons and protons.
That's right. Okay, so in an atom, this is just a simplistic model. Okay? Electrons are going around, and those are moving charges. Okay? Well, is every material magnetic? Every atom has moving charges. So is every material magnetic? No, it's not. So what's going on? Well, if this guy is moving in this direction, this guy is moving in the opposite direction. So that'll cancel its magnetism. Okay? So the orbital magnetism can be canceled. So that can't happen for an odd number of electrons. But if it's in an s orbital, if you have a single for an odd number of electrons, if the last one is in an s orbital, in an s orbital it's really going through like that. It's not going in a circle. So orbital angular momentum is not there. It doesn't give rise to magnetism. Is an electron doing anything else? An electron has spin. Okay? So if there's an odd number of electrons, it has a spin, and it will act like a magnet. A spinning electron acts like a magnet. Okay? Well, if you have paired electrons, the spin magnetism will be in opposite direction, and that'll cancel each other. Okay? So for a material to exhibit magnetism at the microscopic level, each atom is a magnet, and then that's not enough. If one atom is a magnet in this direction and the other one is in this direction, well, they're randomly oriented, and a bulk sample won't exhibit magnetism. Okay, so for a material to be magnetic, the microscopic constituent are magnetic, and they're also aligned. Okay, so but we'll talk about all of that. Okay, so there's a combination of many magnets that are playing in they are in cohesion, and then this sample, a bulk sample, will exhibit magnetism. Okay, so anyway, we'll talk about all of that. Okay, so here is a magnetic material. Yeah, and here are the various shapes of magnets. Okay, so this is the most common shape. Well, in a lab, this is the most common shape that you'll encounter. And a magnet has two poles, north pole and a south pole. Like poles repel each other, and unlike poles will attract each other. So okay. Now, see, charges, electric charges, you can go by a positive charge by itself, a negative charge by itself. Magnets, okay, they seem to have two charges, a north charge pole and a south pole, but they always come together. You can't go to a store buy just a north pole. That is called a magnetic monopole. Okay, and some theories predict them, but we've never seen a magnetic monopole. So magnets the two poles always come together. What happens if you break a magnet?
It makes two more poles.
It,
Just splits them into two smaller magnets.
you get two more magnets. Yeah. Break this guy. Okay, by the way, so this is not right. This is the correct. Okay. So if you break this guy, you get two more magnets. Break that guy, you get two more magnets. till you get to an atom, almost, I mean, loosely speaking, okay? So that'll be a magnet. All right, so here's a magnet. This magnet creates a magnetic field all around it. How far does it create? How far does the magnetic field go? Infinite, okay? So as far as you want, I guess. And the strength gets weaker and weaker, okay? And these are magnetic field lines. So field lines start at the North Pole and end to the South Pole. What are the field lines? So the magnetic field at any location is just tangent to there, okay? And the magnitude of this the magnetic field is greater closer you are to the magnet, and so on. Okay, so let's say this is an electric field. If I place a positive charge here, which way will the positive charge move?
The direction of the electric field?
Yeah, so we saw that the force is Q times E. If you put a positive charge, the force is in the same direction as the electric field. If the charge is negative, the force is in the opposite direction of the electric field. So a positive charge will move in this direction, and a negative charge will move in this direction. Okay. Now, similarly, so now I'll just draw a magnetic field. Okay. For a magnetic field, if you put a north pole there, now you can't go by a north pole just by itself, okay? But if you put a north pole there, the force on it will be in the same direction as the magnetic field. If you put a south pole, the force will be in the opposite direction, okay? So the north pole is acting like the positive charge, and the south pole is acting like a negative charge, okay? So if you put a little magnet here, the north pole is going in this direction and the south pole is going in that direction. So that's how they line up, okay? So little compasses will line up tangent to the magnetic field, with the north pole pointing in the direction of the magnetic field. Okay? All right, so that's how you can map the magnetic field lines. All right, so we saw that these equations tell you these are the causes and these are the effects. Moving charges produce magnetic fields, and this equation tells you how to detect those fields. If you want to detect an electric field, you need a charged particle. A neutral particle won't help you detect an electric field. If you want to detect a magnetic field, you need a charged particle, and it needs to be moving. Okay, so now let's study this part of the equation. Yeah. So that is the force on a moving charged particle in a magnetic field. Okay, so so the force due to the magnetic field on a moving charged particle. Okay, again, this equation tells you if the charge is zero, the force is zero. If V is zero, the force is zero, and so on. Okay, and it's a cross product. Okay, so the force is the cross product of Q times V cross B, V cross B. Okay, so if the particle is moving in this direction, a positive particle is moving in this direction, and the magnetic field is like that, the force is perpendicular to the plane containing V and B. Okay. And here's the way to remember it. Yeah, the right-hand screw rule is the best way to remember it. I'll show you a couple of ways of doing it. Okay, if you turn a screw from here to there, from the first vector to the second vector, the screw would move in that direction. Okay, as you turn the screw like that, the screw would move in that direction. And that's the direction of the force on a positive charge particle. Okay, so again, in a lot of problems, you will need to figure out the direction of the force. Okay, so here's the first vector, there's the velocity vector, here's the magnetic field vector. If you turn from V to B, that's the direction in which the screw moves, and that's the direction of the force. Okay, there'll be times when you won't be able to. Okay, so here's V, here's B, that's the direction of the force. VB, that's the direction of the force. Okay. So you turn a screw from V to B, that's the direction in which the screw moves, and that's the direction of the force. The force on a negative charge will be in the opposite direction. So if a negative charge is moving in this direction, well, you again figure out that vector using the right-hand rule, V cross B, that would be the direction of the force. But if it's a negative charge, the force is in the opposite direction. Okay? All right. So here's, you can use your right hand again. V, the direction of V along your thumb. B is in the direction of your forefingers, and that's the direction of the force. Okay. So this is for a positive charge, and the force on a negative charge will be in the opposite direction. So for a negative charge, you could use your left hand, but I like to figure out the force on the positive charge and then figure out the negative charges, and the force on the negative charge is in the opposite direction. All right, again, the important thing to remember is the force is perpendicular to the plane containing V and B. Okay? All right, here is the magnitude of the force. Q times V times B times sine theta. Theta is the angle between V and B. Again, if you have a neutral particle, the force is 0. Okay. If theta is 180 degrees, what's the value of sine? 0. If theta is 0 degrees, what's the value of sine? 0. Okay. So if a particle is moving parallel or anti-parallel to the magnetic field, it doesn't feel a force. Okay. So you got to remember that. All right, let's look at what are the units for a force. What are the units for force? Newtons. What are the units for charge? What are the units for velocity?
Meters per second.
Okay, so the units for magnetic fields are force QV, Newton, Coulomb, meters per second. Okay. Coulombs per second is called an ampere. Okay. So Newton, ampere, meter. Okay. This combination of unit is called a Tesla, after Mr. Tesla, the famous Tesla, after which the car is named, Nikola Tesla. Okay. Now, it turns out that the Tesla one is a very strong field. A magnetic field of 1 Tesla is very strong. Okay, for instance, in this room, the magnetic field strength is about 10,000 of a Tesla. Okay. So planetary fields, Earth's magnetic field on the surface is about 1/10,000th of a Tesla. Okay. So if you deal with that kind of field, you don't want to write 10,000 of a Tesla all the time. So what do? You invent a new unit and you call it a Gauss. Okay. After one other scientist. Okay. So the SI unit for a magnetic field is a Tesla, and oftentimes you deal with a much smaller field, about a 10,000th of a Tesla, and that's a Gauss. When you get an MRI, we'll talk about these. Those MRI fields are about 1.5 Tesla, and so on. The stronger the field, the more expensive your MRI. See, here's this will give you a sense for the magnetic field. So this is an MRI machine. Somebody turned it on, and look at this. The gurney flew into that. So it's that strong a field. So a Tesla is that strong a field. Okay. So, well, if in the physics lab, in the physics department, there are There's a lab where they have 15 Tesla magnetic fields, so we could potentially try and go there. All right, we will stop here for today. Okay, so just a second, hang on a second. Okay, yeah, so we'll stop here. The units for a magnetic field is a Tesla, and then a smaller unit, 1/10,000th of a Tesla is a Gauss. Okay, we'll stop here.